Okay, I'm going to give an example of how to set up an integral, and just a general way to think about setting up integrals in polar coordinates. Really, what I want to point out to you is that it's not that different from Cartesian coordinates. It seems like it, but there's a way to think about it in a Cartesian way and a polar correction. So think Cartesian, but add a polar correction. So just to illustrate what I mean, I'm going to use a similar region as in the previous video, where we had two circles, and this circle was x squared plus y squared equals 1, circular radius 1. And then our second circle was shifted up. And so it was x squared, again of radius 1, but then you had plus y minus 1 squared. So y was shifted up by 1. And so the region that we considered back then was their intersection. But let's just, for the sake of clarity, let's just consider the region outside the good circle and inside the bad one. Okay, so as I showed in that previous video, if you convert to polar, if you polarize, so to speak, then it is r equals 2 sine theta. That is the upper region. And r equals 1. That is the lower. That is to say, this curve right here, this is r equals 1. And this curve above, this is r equals 2 sine theta. So the first thing you'll see is that this is complicated to look at, because it's not clear where things intersect. It is not, it's not exactly clear which curve is lying on top of the others. Like you'll see that like, it sort of looks like the orange curve near 0 is lying below the black curve away from 0, just because of how you draw it. So to reduce mistakes and add more intuition about what's going on, rewrite it in the r theta plane. And this is what I mean by think Cartesian. Because what we're doing now is we're flattening the curve out. So in the r theta region, we plot both curves as r as a function of theta. And again, we're going to restrict to r positive. So 2 sine theta, let's start with that one. Roughly speaking. And then we have r equals 1, that's our other curve. And as I showed in the previous video, they intersect at pi over 6 and 5 pi over 6. And so our desired region that we want, it is above r equals 1 and below 2 sine theta. Right, so this is a classical type 1 region that we saw earlier in the Cartesian setting. So it's actually not that complicated. It just looks complicated in the polar setting where we were plotting in the Cartesian plane. If we plot in polar coordinates, everything looks pretty decent. So it's classical type 1. So we're going to put the arrows just to keep our integration order straight. So our first arrow will be dr, and our second arrow will be d theta. Remember, this is on the inside of the graph, and this is outside, and this inside-outside stays with the integral. So the theta will be on the outside, the r will be on the inside. So here's pi over 6 to 5 pi over 6. And here's 1 to 2 sine theta. And we're looking for area. Let's just look for area in this problem. We won't make it complicated. So we'll put 1, and then we'll put a dA. So now we need our polar correction. We're going to use r dr d theta, not dr d theta, as in the Cartesian setting. So we're going to replace a dA with r dr d theta, and I'm just going to spread these out to make sure that this is the inside and this is the outside. So theta is on the outside and r dr is going to be on the inside. Okay, so that's our integral, which I'm just going to rewrite on the next page. And then we will put the limits as before. And now, this is just a classical type 1 double integral, which is iterated. And it looks a little different because you have different letters, r and theta, but really it's the same kind of thing. Like, I'll show you. If we do the inside one first, we still have the theta limits, but now we have 1/2 r squared evaluated from 2 sine theta, d theta. And of course, this is 1/2 2 sine theta squared minus 1. And now we're integrating again with respect to theta. So, and this integral is totally doable, right? So this is an ordinary 1D integral. And just to help you out with if you want to practice that, you're just going to use the trigonometric identity sine squared theta. There's going to be a 1, there's going to be a cosine theta, and there's going to be divided by 2. So there needs to be a plus or minus. And which is it? There's a very easy way, in case you haven't seen this before. What you do is just plug theta equals 0. So the left-hand side is 0 because sine is 0. And the right-hand side equals 0 if you use the minus sign. And if you use a plus sign, it's 1. So that's not what we want. Okay, so if you use that substitution, now the integral, oh, I'm sorry, there should be a 2 theta. So if you use that substitution, the integral now becomes straightforward. Okay, so really the content of this problem was, how do you think about polar coordinates? And the key thing is just to Cartesianize it and then add in that polar correction at the end. Make sure there's that r. Okay, hope this made sense and was helpful. Thanks for watching.